Thank you very much for the opportunity to present here our results from our large-scale project. I will talk today about Nucleon structure from simulation of QCD with physical quark masses. My name is Finkenrath. The large-scale allocation of SuperMUC is the major part of the simulation effort by the extended twisted mass collaboration, which has research groups around the world. Basically, main groups are located in Germany, Italy, Cyprus, the United States, and many more. The SuperMUC allocation is a key in the generation of a novel set of cutting-edge lattice ensembles at different lattice spacings, at different box sizes, all at physical light, strange, and charm quark masses. And moreover, this allocation is a driver for new algorithmic developments. The ensembles which are generated on SuperMUC are used in the rich physics program of the ETM collaboration with major impacts in deepening our understanding of the strong interaction part of the standard model of particle physics and in testing this model at the precision frontier. Here I will talk about the QCD simulator, about SuperMUC, how we use SuperMUC for generating these ensembles, and how we tune our simulations on this machine. At the end of the talk, I will give you some insight in what kind of physics you can get out of this ensembles. So why we're doing this, we want to understand the building blocks of the universe, of our world. So basically the fundamental physics of the particles. We can do this by doing collider experiments. Basically what we're doing at the Large Hadron Collider at CERN, or for example, in future collider experiments like the Electric Ion Collider at Brookhaven. We have on the other side the theory, we know the Lagrangian of the standard model, so we can solve it via perturbation theory at the higher energy scale. However, at the low energy scale, QCD, so quantum chromodynamics, becomes non-perturbative. And here, lattice QCD is the only ab initio method which can predict the constituents of matter and the Nucleon structure and phenomena related to the strong interaction. Here we need computation, like we need SuperMUC. Since in the 80s, lattice QCD has been using high-performance computing towards solving the fundamental theory of the strong interaction, the interaction between the quarks and the gluons, building block of our atoms. And it's used supercomputing to predict new phenomena coming from this regime. Since around a decade ago, lattice QCD can be simulated completely with fermions, and it's reaching precisions and enabling ab initio calculations of strong matter and search for new physics. Using dynamical fermions, we have to invert the Dirac operator, solving this equation. Okay, how we can calculate observables? We use a Parseval formalism. So we basically need to solve this high-dimensional integral. It's a high-dimensional integral which can have up to 5 billion degrees of freedom. And we don't calculate this directly. We use this two-step approach. We're using Monte Carlo simulations to generate and to do important samplings of field configurations via the Boltzmann weight by involving the physical degrees of freedom through the phase space by using Hamilton's equation. By doing so, we sample ensemble of configuration on which we can calculate observables, and then primary observables are just given by their ensemble average over this set of configurations. If we include fermions, we need to solve again. We need to invert the Dirac operator. Here, mainly SuperMUC is used for the field generation for the hybrid Monte Carlo simulations. So, what we have to do for inverting? So the Dirac operator is a huge complex sparse matrix. It's a four-dimensional. It's represented a four-dimensional matrix stencil with next neighbor interaction, and it can have dimension of up to 2 billion. So we need to solve this linear equation involved with this matrix. However, if you go to small quark masses, like going to physical light quark masses, traditional solvers like the conjugate gradient solver show critical slowing down. It's very expensive to go to the physical point. Basically, because we need around 40,000 matrix vector multiplication to solve here at this point. However, actually, the matrix vector multiplication is very suitable to scale it up to parallelize it massively. So it was very perfect suited for Blue machines. However, if we go now to SuperMUC, we want to go to larger box sizes to address final volume effects, we need new methods. Such new methods, which are suitable also for SuperMUC, are multi-method approaches. They are based on preconditioning our solutions by effectively treating the large eigenmodes by using smoother, which is shown here, is effectively treating the small eigenvalues, while we have a cross grid correction for the small eigenmodes, which can treat basically, which is based on the multi-grid level by causing the lattice and solving by resolving the problem for the small eigenmodes on the causal lattices. The combination of both is given by the DDR-FMG method, and we adapt this to the twisted mass fermion discretization, which we are using. And you see basically the result. By using DDR-FMG for twisted mass, we can improve, we can speed up the time to solution of our inversion by a factor 100. So we adapt this for our HMC. We pioneered this method in our HMC simulations. For this, if you go to SuperMUC, you have to think about machine requirements. So one thing is you have to think about the scalability. This is limited because basically it scales with the smallest coarse grid, and this coarse grid is smaller. And using domain decomposition, the scalability is limited. So for a 64 cube ensembles, it breaks down around 4,000 cores, while for our largest lattice, which we are using here in our allocation, 96 cube, it breaks down around 20,000. So you have the scaling window, which is decreasing the volume to the power 3/4. Then we have to think about memory requirements. So if you use multi-grid solver, we have to basically save the setup, which comes with a huge additional memory. And this is basically 5 times more than our traditional methods. So this sets a hard limit for the minimal parallelization, given it's possible on SuperMUC. So given for the 64 cube by 16 nodes, with a 96 cube by 18 nodes. And if we use multi-grid methods, we want to be cost efficient, so we want to reuse the setup, this coarse grid setup projection. But this can violate reversibility, and we checked this, and actually we saw that yes, there is some reversibility violation. However, if we increase the residual by a factor 10, we reach the same precision like we would do with this mixed precision CG, and everything which is below this dotted line would be acceptable. Okay. To further improve our algorithm, we can look basically what the simulation costs. We do this in molecular dynamics. So basically, the cost is proportional to the number of steps we have to do. So it turns out that the cost for the hybrid Monte Carlo algorithm scales with the volume, which is a solver, plus a factor which comes from the integrators. And here, this factor is 1/2n. And if n is a higher order integrator, so n is correspond to the order of the integrator is higher, we would have we need less steps. We would be more. We would have better volume scaling. We can reach better, larger volumes. So we tested this. In general, a lot of different schemes available of higher order schemes. What we did basically, we extend our second minimal norm scheme by adding a force gradient term here in the middle. So the C is the force gradient term, which is coming with a second order derivative of towards the action. We compared here on the right side in the test case different order schemes, and we see that basically this force order method outperforms all other methods. Moreover, if you now start to simulate on SuperMUC, there are a lot of different there is a lot of parameters to tune. So for example, the integrators, the number of steps, which we already said. Then we use a nested approach. We use not only one integrator, we used nested integrator approach. So the question is how many integrators you want to use. Then we have on our operator, we use preconditioning. We use Hasenbusch-Marsh preconditioning and rational approximation, and we need to split up these terms and putting them on the different levels of the integrator. So this is basically a multi-parameter minimization problem. So this we solve basically in the prototype version at the moment by minimizing the cost function by at a constant variance of basically a constant acceptance rate. The variance is given here by the variance of the energy violation. So a prototype version for this minimalization scheme is working for this force-gradient second norm scheme and can be applied to all other simulation efforts of the ETM collaboration. On the right side, you see some sketch what kind of improvements you get from this tuning model. It's basically the comparison between the blue bar and the red bar. This gives on the 64-cube lattice around a factor 10%. However, this is smaller on the 80-cube due to the fact that we already, our first guess, our hand tuning was already good. Moreover, you can see other improvements, basically going from Haskell to Skylake, which gave you some improvements, and going from a second order minimal norm scheme, second order scheme to a fourth order scheme at the large lattice size. So let's summarize a bit the improvements which we did. So basically coming from the green, we could simulate a very small lattice at the physical point. Due to including the multigrid, we could improve this by a factor 10. So this was working. We could minimize the cost that we could simulate on SuperMUC. Then adding the 1+1, we could include the strained and charm quark masses. And basically by adding a fourth order integrator, we can now reach lattice sizes of 96. Moreover, there are more improvements to come. We are working in the moment on improvements for DDR5G at the extreme scale. Needless to say, we also need to tune physical parameters of our action. This is basically a very extensive fine-tuning problem, which I don't want to discuss here, but which basically needs to be tuned additionally. This gives us now the possibility to reach a new era of precision measurements in our fields by basically by the end of the current SuperMUC allocation. We will control two major effects. We can take a continuous extrapolation at 3 different lattice spacings at the physical light quark masses, and we can assess finite volume, infinite volume unit by having 2 box sizes at the physical point. The results on the 64-cube lattice are already published. One of these is solving the so-called proton spin puzzle. So before let me introduce this. Before the 80s, due to the success of the quark model, it was believed that the spin 1/2 from the proton is coming from the valence quarks. That this is not the case was found out in an experiment by the European muon collaboration, 1987, which found that as much quarks with spin up are there as quarks with spin down. So it comes out that the spin 1/2 from the proton comes from all constituents of which are in the proton, basically from the valence quark and the C quarks, from the gluons, and from the angular momentum of their different quarks. So we can address in lattice QCD with our physical point ensembles, we can address this in ab initio lattice QCD simulations, and this is our result. So we did a complete quark flavor decomposition of the spin, which requires valence and C quark contributions. For this one needs to calculate disconnected diagrams, which we are doing on GPU machine, mainly on the state. And we include in our calculations gluon contribution to the spin. And it turns out that this is basically one of the major part in this spin contribution, 40%, while the quark contribution is 60%. As a next step, we will use the other ensembles of final lattice spacing that we can take the continuum. So we can say that SuperMUC is an essential part of this puzzle, is an essential of the puzzle stones in this proton spin puzzle. And there are more physics results from the ETMC, basically on these ensembles, which we generated on SuperMUC, Nucleon structure and charges, light, strange, and charm quark masses, flavor physics, and hadron scattering, and many more results are in the pipeline. Let me conclude by giving a short outlook. Next step in simulation is going to larger volumes, final lattice spacing. These are basically extra scale challenges due to computation and algorithm challenges. Larger volumes means we need new parallelization strategies beyond domain decomposition due to longer runtimes. Going to final lattice spacing, we need new disruptive solutions due to slowing down. We are working already on the next generation of lattice simulation software in a project under Phase6IP, where we developed a portable, flexible, modular, and user-friendly Python API, and where we extend the scalability of DDI by adding new cross-grid improvements. If you're interested, we have contributions at the next lattice conference on these developments. So let me conclude. Thank you for your attention. Open questions. Here are some of my collaborators. Thank you very much.